Hello, how are you doing? Today we're going to talk about Dalton's Law of Partial Pressures. And we've heard of Dalton before. Can you remember? Think way back first semester. I believe we were talking about, yes, atomic theory. So Dalton was one of the pioneers of modern atomic theory. He really kind of brought forth the idea of an atom, and that you can't divide an atom into smaller parts without losing what the element actually is. And then, of course, that's mainly what he's known for. But it turns out that with a lot of these people, they do other research, and Dalton actually did a lot of interesting stuff dealing with gas and pressures of gas. So in Dalton's time, it was pretty clear that people could, like, for instance, isolate oxygen. They could put it in a container, and they already basically, because of Robert Boyle, were starting to be able to, for instance, measure pressures. And so they could put oxygen and they know what the pressure of the gas was. But Dalton asked a very simple question. He said, well, what if I have a container and I have, 3, 4, 5 gases in that container? How will that affect the overall pressure in the container? Will the gases affect each other? What will exactly happen? And as it turns out, there's a fairly simple explanation. All you have to do is just add them up. And so I want to show you quickly this little cartoon, but it shows a gas. This is what I call the green gas. It might be kind of hard to see, but it's 200 kilopascals. Okay? And then if you have another container, same size, but you have some red molecules in there, which have a higher pressure of 500 kilopascals. And then you can even have a third gas, what I call the blue gas, and it has a pressure of 500 kilopascals. And so Dalton, again, was wondering, what is the pressure? And it turns out that the pressure simply, when you put them all together, it simply turns out that they add up to basically you add them all up and you get one overall pressure, which is the pressure of 200 plus 500 plus 400 kilopascals equals 1100 kilopascals. So in effect, each of these gases sort of acts independently of each other, and it doesn't really matter to them what else is in there. Together, all their partial pressures add up to the total pressure. Okay, so you simply just add them up. So the next slide here essentially shows the formal write-up of what Dalton's law is. And it states, the total pressure of a mixture of gases equals the sum of the partial pressures of the individual gases. Let me say that again. The pressure of a mixture of gases, the total pressure, just basically is add all of those individual pressures for each of the gases up. And so that comes to a very simple equation. It means the total pressure equals the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on and so forth until you get all the individual pressures of the individual gases. So this basically leads to a formula where if you're given if you have 5 gases and you're given 5 pressures, you just add them up and give a total. Or I could give you a total pressure and some of the other pressures of the gases, and you could figure out the pressure of an individual gas by subtracting. So a pretty simple concept. You will be testing this concept more so just that you understand the basic concept, or even a little bit the formula of how you would actually go about doing this. In other words, I'm not so much looking for an actual calculation, but more so just looking that you understand that they all add up to equal the total pressure. Now I'd like to switch gears a little bit. Oh, I take that back. I actually do have an example of Dalton's law of partial pressures, and its example has to do with air pressure. So let's imagine this is you and you're sitting on Earth, and you are affected by the air pressure. We've talked about that already, and so there's lots of different gases. There's some carbon dioxide, probably a little bit more argon than you thought, and a lot of nitrogen, and thankfully some oxygen so we can breathe. So these are the 4 main gases in our atmosphere: oxygen, nitrogen, argon, and carbon dioxide. Together, they create the majority of of the gases of, well, the majority of what we would call air. And each of them has, as you can see there, individual pressures. For instance, nitrogen, it says it's 590 millimeters of mercury. Oxygen, it says it's 149 millimeters of mercury, and so on and so forth. But can we apply Dalton's law of partial pressures to this information? And so what we can do is try to figure out, well, can we figure out what atmospheric pressure is by adding up these four gases? Okay, so if we go and do that, P total equals the pressure of those four gases, the individual pressures. And so we can just go ahead and add all those up. 149 plus 590 plus 3 plus 8. And then when you do that, you get this number, P total equals 750 millimeters of mercury. So when you add all these gases up in our air, in the atmosphere, you get an air pressure of 750 millimeters of mercury. So some of you might say, well, wait a second. Mr. D, you told us that air pressure is 760 millimeters of mercury. This is only 750. Where's the other 10 millimeters of mercury? Well, it turns out that there's a lot of other gases in our atmosphere. We've put some chlorofluorocarbons into the atmosphere over the years. There's sulfur dioxide from coal-burning plants. There's some bromine. There's some other naturally occurring gases. So there's actually a large number of other gases which would be in the category of other, which all put together add up to about 10 millimeters of mercury. So for the most part, this kind of gives you a feel for where all of that pressure comes from. And most of it's from nitrogen. Okay? Now I want to shift gears a little bit, and I want to talk a little bit about diffusion. This is basically the last part of the textbook. There is a law called the Graham's Law of Diffusion. We're not going to really talk about that in terms of doing calculations. Rather, we're just going to talk about the concepts of diffusion, and then the next one is effusion. And quite often they get mixed up with each other. So I would like to quickly just talk about that. But diffusion is the tendency of molecules to move towards areas of lower concentration and until the concentration is uniform throughout. So one of the more classic examples of diffusion has to do with cell membranes, and you learned in biology that cell membranes are lipid bilayers. They have polar groups on either ends they have polar groups on the end of one and a non-polar group in the middle, and then on the other side as well, and they stack up to make this bilayer. So you have sort of polar group on each side. In the middle you got some grease. And so for instance, when we begin here, we see that we've got an area here, what I would say is high concentration, and down here, literally we have no concentration, so no molecules whatsoever. But over time, by naturally occurring, molecules tend to want to spread out and become more uniform, and so these guys will start moving across the cell membrane, and we'll get a lower concentration here, but the concentration will be picking up, and eventually we'll get to this situation over here where diffusion is essentially complete. We have a uniform concentration, and there's an equal number of molecules on both sides of the cell membrane. So again, diffusion is the tendency of molecules to move towards areas of lower concentration and until the concentration is the same throughout. Okay? And there's lots of examples of diffusion. I mean, if someone comes into this room and has a lot of perfume on, you might not smell it right away, but if they sit there for a while, that perfume may diffuse, and you may be in the back of the room and you might smell a little bit, and someone might say, oh, that's such and such's perfume, and you might even be thinking to yourself, wow, if I can smell it way back here, then it must be pretty smelly up there. So you have a pretty you have a basic concept of diffusion when you say that. And at some point, if this person sits there long enough, all of that perfume will eventually pretty much be spread evenly throughout the room, and maybe at that point we might not even be able to smell it anymore because the concentration might be too low because the volume of the room is so large. So again, an example of diffusion. Now the other area I want to talk about is effusion. Slightly different. And effusion is when a gas escapes through a tiny hole in its container. So normally we talk about having a gas in a tiny hole, and then there's a pinhole, and then some of it escapes and it effuses out. I often think of, I go to France, I get my father-in-law he's French, and he likes really stinky cheese, and he always buys some because he thinks he's being nice to us. And it always comes, and my wife and I, we wrap it in like 3 different bags, and it's sealed. But yet somehow, over time, you start smelling it. And as near as I can tell, what happens is an effusion process is occurring, where even though everything's sealed tightly, a small hole, maybe the bag doesn't hold, there's the space between the polymer and the bag is a little bit too much. And lo and behold, you start smelling that. And then once it gets out, it diffuses in the room, but it originally gets out through effusion. Now the last little point I want to make here before I show you guys a couple of demos is this bottom statement down here that says gases of lower mass diffuse and effuse faster than gases of higher molar mass. So that kind of tells you if you have 2 gases, say, nitrogen and hydrogen, and you have a race, the hydrogen will get across the room before the nitrogen. So it's kind of intuitive, it makes sense, but the lighter gases go faster. Kind of like, generally speaking, human beings, the lighter human beings run faster than heavier human beings. Similarly with gases. So now what I'd like to do is just quickly sort of show you, if I was here I'd like to do it. I know Mr. Babb does this a lot, but it's a couple of diffusion demos, and I have the same demo. One's a cartoon and then one's a live demo. And so once again, I'm going to be experimental here and try to do the YouTube video within a YouTube video. So hopefully this works out. So I'll click on cartoon. Oh, you see it's not working. Let me go back. Click on cartoon demo. And it seems to not want to do that. Let's see. Let's go back one more. Try it again. Well, that seems to be a problem. Try this one. Oh, this one's working. Great. Well, we'll just do this one. Maybe this one will work fine. Let's see. So we have a tube set up, and they've put ammonia on one side and hydrochloric acid on the other. Ammonia weighs about half as much as hydrochloric acid. And if we actually studied Graham's law, we would learn that that distance, the 30 to 20 distance, is actually pretty accurate. And that's actually ammonium chloride that forms from the reaction of ammonia and hydrochloric acid. And so it shows us right where the 2 gases met. Okay. Let's see if I can find my other demo now. So here's the other demo I discovered.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the 2 gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules, relative to those of ammonia, is greater. Thus, hydrogen chloride molecules travel more slowly.
So anyways, that's a couple of the demos. They went a little bit out of order, but no big deal. Kind of gives you an idea that the lighter gas will diffuse quicker, and so when it goes ahead and goes to the tube quicker, it makes the ammonium chloride further closer to the HCl, which is a heavier gas. That's basically all I have for Dalton's Law of Partial Pressure and diffusion and effusion. I hope you enjoyed this recording.